It's now time to look at total internal reflection. And we're going to look at that at a triangle that's an equilateral triangle. So we have 60, 60, and 60 degrees to make it easier for ourselves to understand this idea. So light is going to be incident upon the left side of this prism. And there's our theta incident. It will then get refracted towards the normal, and here's our normal drawn. And it will be incident upon this side of the triangle. And there's our normal. Now to get total internal reflection, we want this angle, what's called the critical angle, that will cause the refracted ray to be perpendicular or parallel to this surface, but perpendicular to the normal. And then light won't come out the other side. It's going to be totally internally reflected inside, okay, this particular prism. So let's see how we can do this. Okay, let's say, we have an index of refraction, n equal to 1.52. And we're going to calculate upon this, and we are going to determine what's called the critical angle here. The angle that will allow the total internal reflection to happen. Well, the emerging angle is trying to come out in air, so then our Snell's law is going to look like this. 1.52 times the sine of theta critical is equal to 1.00 times the sine of 90. And theta critical is going to turn out to be 41.14 degrees. So at this angle, the light will be refracted parallel to the side and perpendicular to this normal. Let's go backwards and figure out what angle of incident our light needs to be on this side of the triangle to make that happen. Well, remember that we need this angle here, which would have been our refracted angle. We'll call that theta sub r. Okay, remember our trick? All we got to do is say theta sub r is then going to be 60 minus 41.14. And theta r is equal to 18.86 degrees. Again, this trick I showed you in a different video, and hopefully you remember how to do that. If not, you can look at that video before this one. All right, so now let's figure out what would our angle of incidence be. So we're coming from air, so we're going to say 1.00 times the sine of theta incident is equal to 1.52 times the sine of 18.86 degrees. And solving that, theta incident is going to equal 29.43 degrees. So if this angle is 29.43 degrees, we will then have total internal reflection on this side. And again, that would be parallel to the side. But what if we want to know do I need to increase this angle or decrease this angle in order to cause even more reflection in? Okay, and let's try getting it reflected or refracted down here. So it kind of bounces around a couple more times, not just parallel. And then when it does that, we'll actually see light inside the triangle. So does this angle need to become a larger angle, or does it need to become a smaller angle? Well, let's increase this angle to 35 degrees and test it. Okay, so we're going to say 1.00 times the sine of 35 equals 1.52 times the sine of theta refracted. Okay, and the second time we're going to see that theta refracted is now equal to 22.17 degrees because we've increased that angle there. So what angle are we incident upon here? Well, we can still use our trick. 60 minus 22.17, and that's going to be equal to 37.83 degrees. So that's going to be a smaller than theta c. So we now know that this angle is less than theta c. So we can already suspect then that means we're going to be refracted coming out here then. Okay, so, but we can actually do that calculation and prove it. Let me change colors so we don't get too confused. So we're coming out to air. Let me do that over here. So we have 1.52 times the sine of 37.83 equals 1.00 times the sine of theta emerging, or we always call the emerging angle when it comes out. And we find that theta emerging is going to equal 68.79 degrees. So what that means is we're going to be coming off here and we're not going to be totally internally reflected inside. So to cause this angle here, we need to decrease the incident angle. So instead of making it larger, we need to make it smaller to get more reflection in there. So if I take my incident ray and go this way, that'll make theta I bigger, and therefore it will actually come out this side here. So we need to take that incident ray and make it go more this direction, and we'll see more light get reflected inside the prism. And that's how total internal reflection works.